For those of you who are not familiar with our group, we're called Dynamic Cast, and it's a peer-to-peer study group created in 2018, I believe, in Berlin, by me and now my old colleague from Ableton, Karen. Well, we actually met at a C++ meetup and decided to create a safe space for people underrepresented in the community to just share knowledge. And the idea was that none of us necessarily play the role of a mentor with mentees. So this was not the split. We just somebody would bring a topic they learned and we would all spread it. Now we also, as of last year, no, this year actually, right? We have a meetup in London as well. So we invite people to join our monthly meetups. Yeah. They're always hands-on, very practical. Right, so that's about us. We're here, the people who have prepared this workshop for you is myself, Anna, and Harriet and Rachel. Harriet and Rachel are the organizers of the London chapter of our group. All right. So we're going to be going through the slides and all these handles and whatever. They're clickable links. So I'd want you all to get access to slides, which may be useful. So if you go to this GitHub repository, maybe I'll just show you what it looks like. This is the repository we're going to be using throughout the workshop. And if you go to its wiki, well, this link should lead you to the slides. So for those who want to follow with slides or maybe go forward or when things are dragging for them because they are more advanced or want to think of problems on their own without having guidance, please feel free to do it by following the slides. There'll be time when maybe this will be useful. Okay, so please feel free to follow the slides on this website. I'm gonna go back to this presentation. Did everybody get it? The link? Okay, perfect. Come on. So as promised, we're gonna be discussing different stages of working with existing code. So roughly, we can name the stages as first, the building stage. We'll have to know how to configure and build our project in order to be able to contribute to it. And then finally, well, make some changes to it, so contribute to it, and then deploy our changes, which is colloquially called shipping the changes. So yeah, let's now have a look at each of the stages. First of all, we're going to be building our project, and for those of you who are familiar with Git and CMake, just feel free to just clone the repo and build it. But for those who will be doing it for the very first time, Harriet will give an overview of what building is, which stages is involved, and how to build our project. We're going to focus on different platforms, so no worry, we're not going to leave anyone behind. But if you know what you're doing, please feel free to just go ahead and build the CMake project. Yeah, thanks, Anna. The microphone? Sorry. Here's one I made earlier.
Yeah, thank you for that lovely intro, Anna. So I'm going to be talking about building a system. So what do we actually mean to build? What does it mean? How do we go from our CPP files, our header files, and actually produce an application that the computer can run? So what I've done here is made a very simplified C++ compilation model for you. So my little log line here was, to build a C++ program means to compile source code from one or more files and then link those files into an executable, a dynamic load library, or a static library. So you've got various targets that you can go for, depending on how you want to ship code or how you want to use it in the future. So these are our 4 steps: pre-processing, compilation, assembling, and linking. And that's how we do that. So just a quick note on pre-processing, that's where we have our source files. So if you've worked in C++ before, you know this .cpp, .h, and it deals with all our includes and defines at the top. So it basically dumps out a huge file of everything and your user-defined macros with the define tags and stuff like that. It all gets dumped into one long file at the pre-processing stage. And then we compile it. So after it's expanded out, we put it into assembly code to output into an assembler file. And I don't know if any of you guys have experience looking at assembly code. It is it's a lot of fun. I remember doing it about 6 months ago to learn about optimizations and stuff. So it's something that can be interesting to do, and you can make your eye target that if you want. But wouldn't recommend it today. I think you don't need to go that deep. And then we assemble. So this is like a really nice diagram that I found on Geeks for Geeks, because Geeks for Geeks is great. And it just sort of shows how we go from source code to object code. So we're converting the compiled assembly code that we've got into object files that the machine can read, basically. So we've got our executable, library file, things like that. And then we link it all. So we need to, I'm sure you've had link errors before if you've worked in C++, right? You get that capitalization link error. It looks really terrifying when it's either you've written one thing wrong or something, or it just can't find a file somewhere, and that's it, really. So this little flowchart here is more of an overview of things like that. So we come out with our object files, which Anna told me last night have different different endings. They're not .objs for everyone, which blew my mind last night. And then they get linked, and then we have here we've targeted an executable file, but like I said, this could be a dynamic load library or something like that. All right, so this is where we come to build systems like CMake. So we use build systems to control builds across multiple platforms. This automates our compiling process. The example I was going to use is, say if you've built a video game, and say you want it on your phone, but you also want it on your PlayStation, or you want it on your PC. A lot of the source code will be the same, right? But you need different things to be able to go from, like a really small memory bank, like a phone or a PC. So a way of automating that is to use a build system like this, so you can target different solutions and stuff like that. So CMake is a generator of build systems, so it generates make files, includes instructions on how to build your code, and can target multi-platform build systems such as Visual Studio, Xcode, and KDE, Velop, and things like that. Obviously, there's a lot more. I just made a small list there for you. The benefits of using CMake, I think I know a lot of people use it. I use it every day at work. The scripting language, I think, is really nice and easy, and the documentation is really good for it. So if you wanted to, say, after this workshop, go a bit further with CMake, they've actually got a really great tutorial on writing in their scripting language, so you can make the CMake lists that are required and things like that. And yeah, like I said, widespread usage. A lot of people use CMake. It actually comes from Make, which was the predecessor, and it was built on with CMake, and it's open source. I actually didn't mention that either, so that's great. We love open source. Okay, so this is where things are going to get fun, because we're going to build an open source project with CMake. I'm sure you've all had the email before, but we asked you guys to install Git, CMake, and an IDE of choosing. And that's what we're going to be using today. And I've recommended using a Git GUI client called SourceTree to interact with GitHub in a way that's not just in the command line, but it's not. We don't need that today, really. But it might be something you want to look at in the future. Okay, so this is the Git bash. There's the link for the Git in case anyone hasn't installed it. Has everyone here installed Git? We all good? I'm liking the nods. Well done, guys. Okay. On Windows, sorry, I'm a Windows user. I'm a Windows developer. I know we're very few and far between. Open up the Git bash if you can, and you will see this screen. Has everyone got this? Obviously, in Unix, you can just open command line, right? And you do it there. Yeah. I'm just going to talk about the repo we're using quickly. I've been told it's pronounced Aquila. I don't know if I'm right, and I'm really sorry if I've butchered that. It's an open source, cross-platform DSP library written in C++. Anna found it on GitHub, and it's got some really nice documentation and stuff. So that's what we're going to be using. That's what we've forked. We've pulled out the extra dependencies so we can just focus on one thing today. Okay, so I'm sure most of you have already cloned the repository, but this is what we're going to be doing now. So what you need to do is create a new folder to place it, basically. So I was just doing that. And then what I've done here is actually written out the command you need to write to git clone. So it's git clone and the URL. So this part here is optional. I wanted to make that clear. This is something that I do to source control. So that will make a new folder, and that will place the code that you've cloned into that folder. And that's a really nice way of making sure that you've got all the source files in one place. And then when you do your build, you can do that in the folder that you've just made. So it's like source file build, and you don't get confused. But like I said, it's completely optional. It's just a workflow that I like to do. And then we're going to look at the command line stuff. Anna, would you like to do it?
Right. So in case you're Linux or a Mac user, you can just execute these commands in your terminal when you're in the Aquila workshop directory. This is my workflow. We may have like conflicting workflows here, but I hope everybody settles on their own one. So basically what happens, like it's a common practice for projects built with CMake to create a folder called build, where all the build files are gonna are gonna land. You enter this folder, and then you execute the CMake command. This like ... is basically a path to the top level CMake lists file, which in most projects and also in our example is directly placed like at the root of the Aquila workshop directory. This is why when we're already in a build folder that we've just created and CD'd into it, entered it, we're just like saying, oh, go to the folder above it, right, where the CMake lists file is, and use it to basically make. And then, since we're gonna be using a debugger later, we're asking you to build a debug build. And you can ask CMake to make a debug build for you by passing it this option, CMake build type. And you pass options to CMake by saying -d and option name later. So that's the command line way of doing it. And then, since we promised to run the workshop in VS Code, which I tried to learn for the workshop actually because I'm a command line user and Vim user, but I don't use IDs. So let's see if that goes well. I had to restart VS Code a few times in preparation for this, and this is the reason why I don't use IDs. But it's wonderful either way. I understand how it's useful. So we're gonna see if we can quickly manage to build this project in VS Code as well. So if you have VS Code installed, you just go File, Open Folder, and navigate to the folder where you put the repository. I already opened it, so I'm not gonna do it. It opens in the left split here. And then, this is what I mentioned on the slide, if you have C++ extension pack installed, which I highly recommend, please install it if you don't, you can go to extensions here and search for C++ extension. Well, I don't know if it's gonna find it since I already have it installed here. But yeah, this is what you're looking for, C++ extension pack. And it also says that it immediately installs CMake integration for you. So if you have this installed, it's gonna detect that it's a CMake project and present this useful panel at the bottom for you. And then we're gonna say here, in this build, we're gonna select the target we wanna build. Let's just build all for now. If you click on it, it's gonna move you to the search bar and you can just search for all. Oh, right. Build all, does it, oh, yeah, so. Why isn't it not working now? Great. Yeah, any idea?
It's targeting generators.
No, I just wanted I want to build all targets, but here it should find me, right? Should show me what targets are available, right?
Click on,
sorry?
click on generators.
Yeah, but this is for launching, right? Yeah, this is for building. Oh God, nothing ever works. Anyway, if anyone has problems with it, we're gonna discuss it. I'm just gonna hit build now in order to trigger the build, and it's gonna start building. Oh yeah, great. Nothing works. You know what? Last time that happened to me, I restarted Xcode and it worked. I'm gonna just try something else. CMake debug, select it from here. Oh, you can find, what do you want from me? Well, just when I default to command line. Classic. Just gonna reopen it, seriously. Yep.
Online said something about maybe you have to select a kit.
Oh, right. Yeah. Fair enough. So I wanted to mention this. Yes, good idea. Yes, I want to mention this, that it's a good idea if you have to select a kit. I was selecting unspecified before to let CMake figure out what what compiler I'm gonna be using. And yeah, exactly. Yeah, probably it's gonna work now. Cheers. Okay, and then yeah, exactly. I click on the targets. I can select all here, and then hit this build here. Oh, great, fantastic. Still doesn't. It's not happy. It doesn't find my LLDB. Good build. Okay, you know what? I'm gonna try to remove my build fold. Oh, live coding always works. Let's see if it's gonna be native kit and select unspecified. Build all, perfect. No, not launch, build here, sorry. Okay, fair enough. Clicked the wrong thing. It was trying to find my debug configuration when they didn't provide it. Sorry, wrong button, build. Not the, yeah, just clicked it wrong. Fair enough. Has anyone had problems building the project or is it, okay, perfect. What about online? Has everybody built it? Yeah, perfect. Once you've built it, I can only recommend running a few targets we've just built. So this repo is structured so that it has a bunch of examples which produce some like funny ASCII art output in the terminal. And every example is set up in CMake to be a separate target. So basically here, if you explore targets, I suggest running generators. You can run it. It like shows you different signals generated by this library has different generators which are like different kind of oscillators, like a sine wave oscillator, sawtooth oscillator, and so on, and stuff like that. So this is just a demo of how it works. Or like you can, I don't know, maybe I think AM modulation had some funny output. So just make sure you can run these examples and play around with this. And we also have an overview for you how to build it using Visual Studio or Xcode. But if nobody had any problems, I just wonder if it's still necessary to go through it. I wonder like if people online can get it to work and can someone speak up, because I think otherwise we're just gonna move on to working with this code. Yeah, looks good. Maybe we can just move over.
I'm actually going through the GUI stuff here.
Ah, yeah? Okay, fair enough. So there are people needing assistance, so Harry is just gonna quickly go through it. Please bear with us.
Yeah, sorry.
Cheers.
So, yeah, we have some slides prepared. How do you go back to full screen?
Just gonna run it here.
Simple as that. All right. So the next slides that I've prepared for you are doing it via the CMake GUI. And as I was doing it with this lovely woman up at the front, I might as well do it for everyone, right? Because there'll be someone who needs this to happen. So what you need to do is open the CMake GUI. Windows users, please run it as administrator because we need to write some files in places that need admin access. And so once you've got that open, you will see something like this. And we know we've got it here. So this is what I was saying earlier about having your source code and builds built separately. So this is what the hierarchy is looking like there. So what I want you to do is locate where you've put your source code. That's what this first box does. Wherever you pulled it to, point it to that. And then make your build file somewhere. Again, I find it's useful to put it in the same place as the source code so you can keep track, and put that there. And then after that, you need to click configure. Is there just one person using the GUI in the room? Has everyone else done it via the IDE?
I think
Are you doing it as well? Have you got this step? Is it going good? How about over here? Are you good?
Yeah, I'm just setting it up.
Fantastic. We'll wait a minute. The GUI is like a really nice way if you're new to CMake to not have to run any command line things. Basically, I actually hadn't used it until last week. I've just been using VS Code before that and the bash when needed. Yeah. So once you've clicked configure, you'll need to specify a generator for your project. So Mac users, that will be Xcode. Windows users, that will probably be Visual Studio, might be C-Line, of course. This stage, it's really important to make sure that you click the correct generator and correct platform, so x64, because if you pick that wrong here, it's going to compile to the wrong type and you're going to get a ton of errors. But CMake's pretty good at knowing what to do standard, so you probably will have done it already for you. So that's what you need to do there. And then you can click generate. You'll see these 5 flags come up, and as you can see, we've ticked them at options, I guess they are. And you can see here, we've decided to put the install prefix in program files here, but obviously you can change that if you'd like. But that's where I've suggested installing things. Yeah, so click generate. It'll probably throw a few MSVC errors because Windows. And yeah, that's everything you need to do in the CMake GUI. I will come over and fix that. Or hopefully I'll fix that. No worries. All right. And then we need to run the build system. So we go into Visual Studio, run that as administrator, open the project and open Aquila SLN. And then all you have to then is go to the pane on the right, and you will see this really long list of targets and things to go to. So make sure you're doing a debug build, because we're going to be running debugs. So what I'd like you to do is right-click on all build and press build, and let that build. And then once you've done that, go down to install, right-click on that and press build. And you should see that it will say 5 succeeded, 0 fails, hopefully. There'll probably be some fails. Hopefully not. How do we tell if it's a successful build? Well, we've told it to install to a place, right? So that should now exist in the CMake install prefix. So you can go there, and if you can find your library files and your include files there, that means that we've successfully built and installed via the GUI, via Visual Studio or Xcode or something like that. So now we can move forward. Would you like to?
All right, so now that we are all set up, let's try to contribute to this repo. So what does it mean to contribute? Well, you can think of it in different ways. You either, in order to contribute, you'll have to first read some code and understand it, to understand like what it's doing and how to change it or add to it. Then you optionally write some code, or actually you may just be deleting code. It's a completely valid contribution to a code base to just delete lines of code. As an example, I have this link to a pull request, which is called remove that code, and it removes 400 lines of code. Great PR. Don't confuse people with your dead code that doesn't do anything. Great, right? So just wanted to demonstrate that your contribution may sometimes mean understanding why something is not needed anymore and getting rid of it. Cool. Well then, let's look at the first part of our contribution stage, which is reading code. And it's important to notice you read in order to understand, right? And everything starts with comprehending what you're saying. There's a study called, there was a paper that studied how much time developers spend reading code versus writing code. And it turns out actually the majority of our time is spent reading code, especially when you work with large legacy code bases. I worked for Ableton Live, I worked on Ableton Live for like 7 years, which is a massive code base that's like 23-year-old this year. And so there's a lot of legacy involved, and sometimes it would take me 2 weeks to contribute a change, which was a change in 1 line of code. So sometimes you find yourself in these situations because the most of the time was spent actually understanding what I'm doing and how things work together. Right, so apparently 58% of our time is spent on program comprehension. This is why I think it's very important to be focusing on it. yeah, it's like, as we mentioned, a prerequisite to be contributing to code, because if you don't understand what you're doing, good luck actually changing what you're seeing. And this is contrary to the common advice young programmers are given, or like fresh programmers are given, because they're given, in order to become a better programmer, you gotta code more. Well, I argue you gotta read more, because reading someone else's code can teach you a lot of new practices. Well, maybe there are gonna be sometimes anti-patterns, but still, you're gonna get better at gathering what you need faster. And also, when you approach a new code base, many times it's gonna feel extremely intimidating. It's gonna feel, oh God, I wanna like scream and run away. I'll never figure it out. Well, the more you stare at it, like, you know, the more you start grasping concepts using it, seeing like patterns people were following, the easier it's gonna get over time. So if you're new to this world, please don't worry, please don't panic. It gets better with time. There's a book called, like, I think it hasn't been officially published yet. There are like first drafts of a book called Code Reading in Practice, but Feline Hermans, who studies actually cognition of programmers, like how we, like what cognitive abilities do we need in order to comprehend code. And like she defines different dimensions of approaching code. So you focus on the structure, or on or trying to learn more about the domain, or like concepts, context, collaboration. I think it's all like very interesting to keep this in mind when you approach code. What am I trying to do? What can I hold on to, right? What is there what techniques I can use to reason about this code? So the advice we're trying to give you here is practice reading and reasoning about code often. Like, yeah, maybe if you, even when you're like new at work, you can just go through other people's pull requests, even if you don't review them, just to familiarize yourself with what people do and how they do it. And ask questions, why did you do it this way, right? And stuff like that. So that's very important, and this is actually what we're gonna be focusing most on today. So, as I said, it's good to know what you're doing when you're approaching code. And also please note that there are so many ways of doing things that everything we're presenting today is just a proposition. There's always gonna be different strategy you want to be using, but I think what's most important is always to remembering why I'm doing this. What am I trying to accomplish, right? So a lot of new programmers get completely distracted when they approach a new code base, being like, you know, I can make a comparison to a Wikipedia page. You enter Wikipedia page and it's like, I wanted to learn about this. And then you get lost in the links to other things, right? Oh, what is this? What is this? What is this? What is this? Three hours in, you're like, what was I looking for? Why am I here, right? It can be the same with code. It often is, right? So depending on what you're doing, you may want a broader understanding of the domain, or you may not. Maybe when you're fixing a problem, you want to go depth first. Okay, what's going on there? What's going on there? I don't know, but I don't care. I actually have to narrow my focus and go just deep first to see what's causing my problem, even if I don't understand what this problem is about, right? So, for instance, I think like bug fixing is a good example of this. When you approach a code base and you just want to find this faulty line of code that's messing up with your code, you don't necessarily need to understand how the algorithm works. You can reason about values, right? So, and then build up the understanding maybe of the algorithm if you need it. Maybe you just don't need it. Maybe it's like a very simple fix after analyzing the relationship with values. But sometimes, maybe you want to go breadth first. Why would you want to do it? Well, maybe when you want to integrate a completely new component with a code system, right? So you just need to find this entry point, or just like hopefully in a nicely structured code, a very thin layer which you can use to like plug in your new code. But then you would want to see how other components are created, what they do, where your code belongs to, right? More on like a structural level than, you know, instead of getting lost in details about how things work. And exactly, so you don't need to understand all the details, how a component works. You want to understand what components there are, right? So you approach reading this code completely differently. You're like, oh, okay, I don't know what it does. I don't know what it does, next, but I create a graph of the architecture, what components there are at all. Right, these are just like 2 examples of when you would use which technique. So what I'm trying to say is that always go back, remind yourself, why am I here? What am I doing? What is that thing I actually really need to understand at this time? All right, so depending on what task you're preparing to do, this decision may be different, right, as we said. So as mentioned before, if you want to fix a problem, maybe you actually don't need to understand a lot. You just want to go deep head first. Maybe you will, depends. Then if you integrate, as we said, well, maybe you just need to understand an overall architecture without the attention to detail. When you want to modify, well, it depends. Should probably mixed, right? It's like, probably you have to go like, understand like only maybe these 2 components, right? And go deep in one of them. So this is gonna be a mixed model. All right, so what's gonna be a better way of practicing it than debugging and fixing a problem? So we created, well, if you go to the original repository that we modeled our repository on, because as Harriet mentioned, our fork is stripped of third-party dependencies that would make you just like install more stuff. If you go to the original repository and you go through their issues list, there is an existing issue that somebody reported, which says bad access error when reading WAV files in a loop. And if you read it, somebody says, I'm writing an Xcode project to read a large amount of WAV files in a loop. After reading each file, I proceed to calculate the MFCCs. I randomly get a bad access error for the MFCC object calculate function. Does anyone know how to solve this? Well, when you see a problem, the first thing you do is try to reproduce it, right? It's like, I don't know what caused it, but I need some code that will get me in the same state as this person is reporting, right? So I did the work for you and wrote some code that's on the branch debugging. So I'm gonna ask you all to check out the branch debugging on the repo, on our Aquila workshop repo, and build the workshop target. I put it in an example folder as yet another example. So modeled after like the already existing architecture, it also became like, I made it a separate target. So you build the workshop target, and then we're gonna run the workshop example, and we're gonna pass as an argument tone.wav file that's in the examples workshop folder. So in Xcode, if you go, well, wherever, but like I'm gonna use Xcode to navigate through files. If you go, well, I'm gonna check out the French first. And now we have a workshop folder in the examples folder, and there's this tone.wav file here, right? So now if you're familiar with debugging problems and you have your debugger set up, this is fantastic. If you don't, and you're using Visual Studio Code, it's gonna expect you to have a launch JSON file. And what we can, like, where are the slides? I prepared for you the configuration you may want to use. The top one is going to be for Windows users, the bottom one for example for Mac users. And I already put the config here so that the current working directory is the workspace folder, so the top level Aquila workshop directory, and then these arcs should work and navigate you to the sample we're going to be using for this example. And yeah, hopefully the debugger is going to find it and fetch it and use it as an argument for for the application. So we can either build it using Xcode. If you're using command line, you can code the build directory. You just say make workshop. Woo. CMake. Debug build type, yeah. So we're gonna reconfigure for it to be able to find the new target workshop. And then make the thanks. Work. Examples. Workshop, right. How come? I'm just gonna redo it. All right. So once we've built the workshop target, it can take a while. This library is not big, but we wanted it to have some stuff in order for it to feel like a big-ish existing code base. And then if we build this target, we're gonna have an executable in the examples folder. Sorry, in the examples folder, we're gonna have a workshop folder, and this is where our executable workshop is. And then we wanna pass it what was that, tone, right? So we're gonna execute this. Yeah, and we get a sec fault. And I would want you all to be at this stage. Sorry for sec faulting on your machine, but that's what we're gonna be dealing with, and I'm gonna attempt at reproducing it in Xcode, VS Code, sorry. So in order to do it, I need a launch JSON file, right? So VS Code is expecting me to have this file in a directly called VS Code. It should automatically create it for you if you click here and say, maybe just like, yeah, create a long JSON file, but then you'd want to choose a debugger and it's not seeing my debugger, so I'm just gonna do it manually, okay? If it's showing you, like, please, you know, use the tool, but anyway. So I'm creating this VS Code directory at the top level, and I'm just gonna create a long JSON file in the VS Code directory. And now, put the stuff I put in my slide here, right? Save it. And then hopefully, when I go to the debugger, yeah, I'm gonna have these configurations seen in here, and I'm gonna choose the LLDB one, since I'm on a Mac. And I wanna change the target to workshop, as I said. And then it's gonna be great, didn't see it. Oh my God. Okay, you know what? I'm not friends with a VS Code, clearly. Fair enough. This is a warning, isn't it? Yeah. Kid unspecified. And then fantastic. What if I build it fully through? specified, build, fair enough, build everything. Workshop. Here's the workshop. Now go to debugger, launch mine. Great. Paused on exception. Fantastic. Thank you, VS Code. I appreciate it. All right. Okay, so who can tell me what's the bad access error about in general? Not in this particular. Does anyone know? So bad access error, sorry? Yeah, that's really nicely noticed. And what happens? So like somebody said here that is an invalid index, right? So let's see. What we can see here, we can immediately use the debugger to explore the data we have available here, right? So there's some sort of like apparently an array called named A, and somebody's trying to access its index J, and the value of this index is this big number, right? And it's saying, or maybe it's referring to this J1. We don't know which one. This just shows that it's in this line. And it's an even bigger number. And it results in bad access error. What is bad access error? Bad access error is thrown. Well, it's shown for us when we're trying to access part of memory which is not for us, basically. It wasn't assigned to our application, right? So you're like outside of the memory that was allocated for us. So it's like, hello, no, not for you. And what happens when we actually are trying to access something that's not for us? Or like what happens if you're trying to access the memory that's within the bounds of the memory assigned to our application, but we didn't initialize it ourselves? When we're trying to, sorry? Potentially, right? We read garbage. Or it can just so happen that it's initialized, this memory is initialized to something maybe meaningful for us. Maybe, or maybe it's garbage. So it's called undefined behavior. We don't know, right? So we're potentially hitting undefined behavior here because like we're trying to access something that's, that we shouldn't have access to, which like we're, you know, it's not giving us access to. But if we did have access to, we could not rely on this data being meaningful for us. And therefore, this is, yeah, undefined behavior. All right, so probably the hunch, we can like reason about it and say that this index is outside of this array's bounds, right? So now we just have to find out why. And this code is so approachable, right? So this is where the fun begins. This is when we scream and want to escape, or we patiently push through and hopefully figure out what's going on. All right, so maybe like a quick intro to what a debugger is. It's an environment that helps us reason about code. So here to the left, you have a list of variables within the stack frame. What it means, it's just like at this point in the debugger, like the code knows about these values listed here and we can explore them. So like for instance, oh, the value J was assigned here and we were past this point, we can read what its value was and so on. Everything that was defined until this point, we have access to, we can like, yeah, query these values. Cool, so that's useful. What else is important here? Well, this thing called call stack is going to be very important for us. What is call stack? Well, there are two approaches to reading code in a situation like that. One would be the linear approach. So like you basically start here and go back or forward and reason about this code. And this is what people usually like automatically do. We like naturally think like, oh yeah, I'm just gonna read everything around it now because this is what like reading text is like, right? This is how we read books. But it's not always useful when it comes to reading code, right? What is more useful is to see what called this code. And this is what call stack is for. So here in the debugging, we can jump. We're like, okay, we ended up in this place, but what brought us to this place? So we were, let's just scroll up and see what is the name of this function we're in. It has a lovely, friendly name, CFTMDL, which usually we can learn a lot about code by reading the names we have available, documentation we have available. Well, it's not the situation we're in currently. So we can't hold on to this, unfortunately. But we say, okay, we're in this function called CFTMDL. We can see it in the call stack. This is where we ended. And it says, well, you're in this function. It's defined in this file. And the problem is, like, you're currently stopping in this particular line, right? This is the line number. Cool. Well, then if we go down the call stack, we see how we entered there, how we ended up there. So we were in this another lovely function, CFTB sub, self-explanatory, what it does, and then ended up calling this other function here. Cool. How did we end up here? Well, we called it from this other function, and then we noticed that the next line in the call stack comes from a different file, right? So like now when we look at this file, some sort of like a C file, if you hover over like the name of it maybe, it says that it's like defined as like lib, ura, blah, blah, blah. It's a third-party library, right? So this like Aquila, right? framework just actually has two dependencies. If you look at the files, there's a lib folder, which has two subfolders. One is ura, one is called unit test pp. So basically there are two external dependencies pulled into the repository. One is for the fast Fourier transform, the other one is for unit testing, right? And we end up in our call stack in this third-party library, which means, well, probably should work. So probably the problem is not in the library. Maybe it is, right? Or maybe it's on our side, right? There's a problem in the framework or somewhere in our code. But even if the problem is in the library, good question if you want to change the library, like the library code, or do we want to work around it? These are all the decisions we're going to be making, right? All right, let's see how we ended up calling into this library. Well, we go down the call stack, and we see that we're already in the Aquila namespace, which is, well, okay, we're back in our project that we are trying to contribute to. Well, this project had this FFT function, right, that does some setup. And then it says, let's call the C function from Ura's package. Okay, this is where you call into the third-party library. Cool. But how did we end up in this FFT function? Well, we called it from MFCC calculi. I was like, okay, how did we end up here? Well, and that gets us back to the code, which we should have started from actually exploring. This is the code we compiled or are running as our example. This is the reproduction code for a problem. So when we go back to the definition of the problem, it says, after reading a WAV file and calculating MFCCs, I get a bad access error, right? So somebody is wanted to read a WAV file, this is what we did, and is creating MFCCs. What are MFCCs, right? I'm deliberately not explaining everything at once because these are just the situations we may end up in new code bases that are new to us. We don't know the names, we don't know what it does, and now we have to decide how important it is to us to understand every single component, right? So if we go to this MFCC, go to definition, we have like a short explanation that MFCCs are like some sort of coefficients that are commonly used in speech recognition. We don't really need this, but somebody's calculating it because it just so happens that these coefficients are useful for giving us some information about spectral features of an audio sample. It's useful for speech recognition, similar classification use cases, right? It's just like, this is knowledge we don't need, but just to set up a problem, right? MFCC stand for male frequency capture coefficients. And what it means basically is like, whoever attended Rachel's workshop before knows what a spectrum is now. We represent this spectrum in something called Mel scale. And the only thing need to know about this is that this scale represents frequencies in a way that's more similar to our human auditory perception, right? And we calculate some coefficients on top of that, and they just better represent how we perceive sounds. So for instance, for similarity, like for instance, you have Spotify radio, whatever, which selects you music that's similar to you, right? Also looking for sounds that are similar to what you're already hearing. Well, when you're like trying to find sounds that are similar to what you're already hearing, you many times are actually also using MFCCs, right, as like useful information, being like, oh, if these coefficients are like similar, then maybe I'm listening to something similar. There's just like some set of data that's useful for these applications. Never mind, somebody tried to calculate them and then ended up in this problem, and now we have to know why. So let's look at our calling code again. So we're reading our WAV file, and we're trying to calculate these coefficients. If we look at the constructor, it says that it, here, wait, what? I just go to the definition of the class, and the constructor accepts something called input size, right? So we have to give it some input. What is this input? Well, it says, it passes it, it just like stores it in a member called input size, and it passes it on to this MFFT object, right? And it uses it somehow. Okay, well, so you want an input size. What is the size of our input when we're reading from a WAV file? Well, the number of samples, right? So we're reading, like, basically a WAV file is represented as an array of numbers. And then we're just like seeing how many of these numbers we have. And this is the length of our input. We pass it to MFCC, cool. And then we call calculate on MFCC. And then it's like, we pass it WAV file. Let's look at the calculate file, because this is where our problem begins. So calculate files wants to have, like, receive something called source. And we're passing it the wrong direction. We're passing it the WAV file, right? So it's like, okay, this is of type WAV file, and this MFCC calculate function wants us to pass something called signal source. Well, then we can already reason about it, being like, okay, probably this WAV file, inherits from signal source. Cool. Well, then a WAV file is some sort of a signal source. Perfect. So let's go back to the faulty code. This MFCC calculate function accepted a reference to our WAV file, and while you pass it a number of MFCC features you want to get, or if you don't pass it, and we didn't, probably it's like defaulted to some number, right? We can double check it, but going to the declaration of this file, didn't jump. So in the header of this mfcc.h file, we see calculate, okay, fine, defaults to 12. Perfect, never mind. Do we actually need this information? Probably not. Cool. All right. So what have we learned now? That here the source is, again, the source is, we passed it here. It wants it to be source. It's this instance of a WAV file, right? Cool. And then we are calling toArray on it. All right, let's see what that is, right? So we go to source, toArray. Let's look at the definition of it. And it returns, it says something like, return sample data, read-only, as a const C-style array, right? And it's a simpler explanation because vector guarantees to be contiguous in memory. We can return the address to the first element in the vector, turn it into C-style array, and like just know that, yeah, our vector and our C-style array is gonna like point to the same elements, which we can already start reasoning about it and being like, oh, probably data is a vector, right? We hover over it and it says, yeah, it's a vector, cool. All right, so what is this vector? What is this again? Well, let's go back to the calling code of it. So in our call stack, we're going to calculate again. Okay, we called it on the source, which is our WAV file, right? So we can already start having an idea of what this mdata is holding on to, right? But we're gonna double check, right? So if we go to the definition of the source file and look for, yeah, mdata and jump to the definition of it, it just says, okay, actual sample data, right? So somewhere upon constructing our WAV file, our WAV file object, we read our data into this array, right? That's what we have just learned. We can go down the rabbit hole and figure out where, and maybe, I don't know, we would want to do it. And maybe it's a good idea to actually do it now so that we learn how to set up breakpoints. So basically, setting a breakpoint is telling the program where it should stop the execution, where we rerun it. So I put a breakpoint here, and now I use this icon to rerun my debugger, restart my debugger. And it's gonna stop here. It stopped here, right? And now I wanna see what happens when I'm constructing this object. So I'm gonna use this arrow down here to step into. It's usually like if you're working from like command line, use debugger from command line, it would be S. So we step into it and we say, okay, what happens here? Well, I'm calling this load, right? What happens when I call this load? Well, I pass it a file name, and then, oh, I'm doing something with this mdata. Cool, I clear it, and now the debugger is stuck because, thank you, VS Code. So I'm gonna, fantastic, I'm gonna restart it. Sometime, oh God, sorry, again. No, it just sometimes hangs. Just, yeah. So, right. So here, I'm just saying, okay, so I'm doing something with this mdata. What else am I doing with this mdata? Well, I'm passing it here, right? Am I gonna end in this part of the conditional statement? Let's see what channel is, right? I'm here and I can reason about this data I have here. I can see what values are held in the left panel. It says channel is left, fantastic. Well, I'm gonna end up in this block then. And it does something with this mdata. Okay, I'm gonna explore this. So I'm gonna put a breakpoint there, continue the execution. So hopefully it's gonna start there next time and it hang again. So I'm gonna restart it again. Sorry. Pass the execution. We ended up here. And now I'm gonna see what happens inside this read header and channels. Well, I step into it and I'm seeing that if we go back, we're passing mdata as the second argument, right? Second argument, left channel. All right, so we're reading into the left channel. Fine, and then if you look at it, let's not like analyze it too closely, but let's see what happens with this left channel. I can even search for it. Oh, I'm resizing it to the channel size, which is read somewhere from the metadata information of the header of my audio file. And then I'm reading into it. I'm reading this data that I got from the file into my left channel. And this left channel, as we remember, is mdata. That's what we passed it. Cool. So going back to where we start, because we have to remember why we're doing this. Now we know that when we're, I'm just going to put a breakpoint here where actually the problem was. When we called MFCC values calculate, when we pass it the WAV file, right? I'm just going to rerun it. Without these, without this breakpoint. I'm gonna rerun my application from the beginning. Okay, so I'm passing this calculate function. Let's step into it. My WAV file, which I now know is an instance of it's a subclass of a source file. Oh, come on, hang again. I just put it manually there, MFCC, calculate, I'm gonna put my breakpoint here. This is where I wanna end. Remove it from here. Right, so, unbelievable. Sorry, it happened to me with Xcode many times. Just keep refreshing it. Right, so, I'm reading this to array in the source, which again, to refresh, if we jump to definition, is giving me a pointer to mdata. Okay, so mdata is my actual sample data. I'm giving it a pointer to it. Fantastic. What can I also reason about this mdata? It's a vector, so I want to learn what the size of it is, right? So I'm just gonna query it from the debug console. I'm just going to say mdata.size, right? Oh, and it doesn't return it for me. Great. Oh my God. Okay. Well, then I'm going to put a breakpoint here and try again. Try restarting. Oh, it's giving me a hard time. Restart. Stop where, oh, yeah. I wanted you to stop here, fantastic. And now it managed to query some information about it. And I can inspect mdata here. So mdata, it says, has this size. 529195. I'm not gonna memorize it. So I'm gonna open a notebook and put this size here, right? I did it before, as you can see. So, okay, I put the size here, put it aside. I'll compare it later. All right, so I learned something about what I'm passing to the calculate function that I'm actually interested in. So, just to recap what we have learned. The source.array is a pointer to the sample data of our array file. And the size of it is this. We wrote it down. Cool. And this is what we pass to the FFT function. Great. So let's just try to reproduce our problem again, because I don't know if you follow, but I already forgot where we're coming from, right? So I'm just going to reproduce the problem again, hopefully hit the same bug. Okay, and go up the call stack. So the reason why I ended up there is because I was here and I didn't know what brought me there. And now I know that the MFCC calculate function calls the FFT t function and passes it a pointer to our WAV file data. Fantastic, right? So the thing that ends up here is the C-style array. Great, is a pointer to my actual WAV file data, what I had here, read into here. Great, that's already something. And I know that the size of it is this number. Awesome. Well then, that's what I know. But why do I want to know it? Well, let's go back to our problem. So in our problem, we're trying to access something from the A array. What is A, right? So A was passed as an argument to this function. Okay, let's see what passed it there. Well, the calling code just is passing it through. It was already given it as an argument. Cool. Coming up, this is also passing the A as an argument. Fantastic. Well then, here, I'm passing this A. Where is it coming from? Oh, I'm constructing it before, right? Okay, cool. Let's see how I'm constructing it. And just to tell people, if you don't follow and so on, the most important thing is to like spend some time with the debugger and see how you can jump and stuff. So don't worry at all about like actual nerdy details of this. The most important thing is to just like jump around, read the values, see how the debugger works, okay? This is actually what we're trying to show people. Fair enough. Okay, so we're constructing this array here. So this is the size we're giving, some cryptic n. For now, we don't know what this n is, right? And then we can see that we're going through all elements of it, copying the value from the array we passed, and was like, oh, we're copying our sample data here, right? And then every other argument is zeroed. And if you read the description, it just says, oh, it's a temporary storage, and it's like, these values are real values, and the other values are imaginary components, and they're zeroed for now. So what does it mean? Oh, we're changing the representation of our sample data to complex numbers, right? But for now, so a complex number, as like Harriet and Rachel were already explaining, consists of real part of the value and imaginary part of the value. So basically, instead of having one values, we're having like twice as many values now. We're only copying the value to the real part of it, and imaginary is like zeros for now, right? Perfect. So, which means that we had this, like our data is going to be twice as long now. So this is why we're creating this array that's twice as long and copying these values here. Cool. So going about this code, we think, okay, in order for it to work, since we're accessing the data to this n has to be at can't be higher than the size of our M data array, right? Because otherwise we're going to be accessing the memory that's not initialized, right? So it can be lower, but can be over the bound. Okay, so what is this n then, right? We would expect it to be the size of our array. So this, is this true? We look at the values we can expect here. Can we actually query it from the console now? No, it won't let me. Anyway, I'm gonna stop here then. Debugger. And rerun it. Maybe VS Code will catch up with me. Well, in fact, it did. And it shows me that the value of n is this, right? What it also shows me here is this n is a member of my object. Okay, so where does it come from? Can I actually jump to the definition of this? I don't know. Yes, fantastic. So this is a member of the FFT function, and we can see that this passed upon creation. All right, when did it get passed? Well, I can explore with a breakpoint. Great. So I stop here and I see, what did pass n here? Oh, okay, when I was creating this URFFT class, it is a subclass of this FFT class, so it passed it to the base class constructor. And when you go up. Okay, this is the code we've already seen. We're creating MFCCs, and this is passing this value to the MFTT. Okay, so after this long, tiring journey, we know that the size of n, which is this FFT size here, is the same size as our sample count. Why? Because this is what we passed here. All right, so basically what we know now is that when we created an instance of this object, we passed this number, which was the number of samples that we queried, and it got stored under this name n. And then when we passed our instance of wave file, it queries its data. Where was that? Right here. And this data was the same size. Okay, so we should be good. All looks reasonable for now, right? So going back to our initial problem, if this, so I'm just gonna remove it from here, remove the breakpoint here and rerun so that we reproduce where we were before. So we go back here and we say, okay, the size of our array we're passing here is the same size as n, what's in n, so we should be good. Where's the problem then, right? So this is what we have already learned. Do you have questions? Well, probably there are many questions. I know it's very confusing, but this is also one other reason why we should practice debugging a lot. It's extremely hard, especially when you have so many layers. Debugging is hard. But as long as you can reason about things and just go back in loops, go back, read a value, go back, right? Reproduce, go back, see what you've learned about this code. You're gonna end up nailing it. But it's very hard. It's just what it is, right? So still, what can we reflect on now? Well, we can say we don't know how the FFT function works necessarily. We don't understand what it does, but we understand what the values do and what the relationship of them is, between them is. And that's the most important thing. I don't even know what it does, but it doesn't matter. I'm already trying to understand if the values are correct, right? So this is when things get even more complicated, and I apologize in advance. So we create this A array, which is how big? It's twice as big as our WAV file, right? As the samples of our WAV file. It's twice as big. And we pass it here. All right. So let's see what happens when we pass it there. Can you go there? Cool. Well, okay. We ended up in this problem again. So let's go back to what brought us here. So here, we will try to understand why J gets out of band. Are these indices wrong? Are they correct? Why are they so big? Well, and this is when, in order to reason about it, when the code is so cryptic, there's pretty much no other way than taking a piece of paper and a pen and just writing things down, how the values change. And it's very tedious, but this is what we're gonna do in this situation. And like, seriously, don't worry if don't worry if you don't follow. But like, what we are trying to understand here is, well, we know the size of our A. We don't understand how the indices change, right? Why are we going out of the bounds? What do you want from us, right? So if we think of it, a fix of it, it was like we would not end up with this problem if this array was bigger then, right? But like, is this what the problem is? Let's find out. So in order to understand how these indices change, we're gonna see how they change. Okay, so there's some kind of J, and it depends on KM, L, KM, whatever. Okay, what's K? You're going up. K depends on N and M2. What's M2? Depends on M, what's M, and we like go up until we understand what these values are, and we say, okay, this M, which other things depend on, depends on L, and L is passed as an argument. So what is this L? I go back. Okay, it's created here. So basically, let's see what situation we're in here. We're passing it, we have this N number. What was N? Let's go back. Oh, it got passed to this function. What was N here? Oh, it was 2 times N, which is twice as big as which is twice the number of the samples in our WAV file, which is the size of the A array. Okay, cool. So when I go back to this cryptic C code, I'm like, oh, the N, I know is twice the size of my WAV file, is the size of the A array. Okay, cool, that's good. What else did I want to know? Okay, what's L? Well, L is this value that is at first 8. And what happens with it then? Well, in here, since I would want us to reason about some cryptic freaking values, I don't think it's very useful to be reasoning about them when they're so big, because L changes in a way until this condition fails. So this number, and I'm going to explain what it is in a second, is less than N. And N, in our case, is how big it is? 1,000,000 something something. And I'm like, I don't want to go through so many iterations to figure out what it does. And my solution to this problem, when trying to understand what these numbers are, were to create a different test sample that's much smaller so that I can actually reason about these numbers, right? So I did it, created the sample, and it's in the workshop folder, and it's called short tone. And I would want us to run the same example with passing this other sample. And I don't know if you remember, for those who are using command line, you just pass a path to this other sample. For those using VS Code, this is where, if you're a Windows user, you change the path here. I'm gonna change mine here because I'm a Mac user. Short tone. And I'm gonna rerun. Sorry, I rerun the same debugger. I have to actually rerun the whole application, which gets passed a new value as a sample. Don't forget to save. I just forgot to save. Cool. So stop the debugger, and I'm gonna run the debugger again, and I hope this new configuration is gonna be picked up with a link to this other shorter sample. Cool, let's do it. Bam. Did it actually put something in the... Oh, fantastic. Oh, I had this breakpoint set. I'm just gonna deactivate it and rerun it again. And what happened? Okay, I'm gonna demonstrate it again. I rerun the same code, which was this is the code, it was the reproduction of our problem with a much smaller sample. And my debugger is running, it stopped running, and it didn't stop in the same place. It executed it, and it actually spit out me the coefficients. So it didn't fail. And we're like, what? Right? It's like, what on earth? So let's see what the number of samples is. Let's explore it here. The number of samples is 520. Okay. My code didn't fail. what can it mean, potentially? Well, it can mean this code only fails for big sample sizes, right? Or for particular lengths of sample arrays. Or, coming back to what we talked about before, it can mean it's an undefined behavior. Sometimes it works, sometimes it doesn't. Sometimes, if it accessed memory outside of the array bound, but it just happened to be initialized to something meaningful. Sorry? You're crushed? Okay, cool, let's go. Yeah. Undefined behavior, mine didn't, you're crushed, right? Fantastic, perfect, great problems. We love them. It's great to spend 3 weeks of your work with these kind of problems, right? So, the problem is that many times there's like no reliable reproduction scenario, right? Sometimes people run examples in a loop, maybe as the person who reported this problem, right? Well, I read files in a loop and sometimes it fails, right? Well, this is one of the nastier ones. Okay, but a great example of undefined behavior, by the way. So, but why did we even start it there? Actually, we did because we were interested in what's happening here, right, in our code, and to reason about the values. So I'm going to put the breakpoint back there and restart it. We're going to follow, finish soon and have a great break, so don't worry. So let's see what happens. I'm going to continue playing this code. I end up here. So I'm thinking, okay, one of my assumptions was what if actually it worked for this size of an array, right? So what we said is that what we already discovered is that this number n passed to this function is the size of our A array, right? What is n? N is 1040. We just inspected before that the length of our sample is 420. Makes sense, right? It works, okay. And we're trying here to access an index 140, 112, whatever. Okay, this is within the bounds. Cool. But this is just, I just put the breakpoint in there. So this is just the first iteration of this loop. Okay, I'll just keep stopping there as I go through the loop and see how my values change. Right? I can see to the left that these values change. They go bigger as I go through the loop. And then, okay, great. I can see how far I can go. Okay, they get higher and higher and higher, fantastic. Will they always be within the bounds? Well, I can either keep pressing this thing or I can start reasoning about the values, which we're gonna do in a second, right? Just press it a couple of more times. Fair enough. 1040 was the maximum index. Are we gonna exceed it? Stay tuned. We're getting close. 954, fantastic. And wow, we exceeded. Right? The J is 1056 and it doesn't crash. Right? I want to query the value of this, A on the index of J. I don't know if Xcode is going to let me. 0. Oh, wow, it works for once. The value is 0. Okay, so it just so happened that this memory that I should not have access to is initialized to zeros. Right? So it doesn't crash for me. But it's random. Okay, well, so now I'm going to be stubborn and reason about the values. So what do we said? We said that we're curious about this L value before. How does this L value change? And what I would do is I would take a piece of paper and a pen and see how this value changes. And I'm just going to do it in this equation editor here. And in here I modified this spacing browser inspector for it to be bigger. So maybe I'm gonna erase this one. Great, so L is 8 at the beginning, right? And how does it change? Well, okay, what is this condition? L lower than 2. Do you know this operator? Yeah, exactly, it's a bit shift. Yeah, what does a bit shift do? Well, maybe it's useful to, I'm just gonna show in Python, right? So L is 8, right? And I want us to see what the binary representation of it is, since we're talking about bit shifting, so we're in the binary domain, right? So when I say bin of L, or bin of 8, this is the binary representation of it. You can skip the prefix 0b, just stands, this is a binary representation of a number. It's 1, 0, 0, 0. For those who don't know binary, it's like you read it sort of like from the back. Like the last digit is to the power of 0, so 1 plus 2 to the power of 1, plus 2 to the power of 2, plus 2 to the power of 3, right? So this is 8, because it's like 2 to the power of 3 times 1. It's always like times whatever number is here, plus whatever times 0 is 0, so it's 8. And now, bit shifting, so I'm just gonna use this string, right? Bit shifting, if it goes like to the left, is like we're sort of moving the whole value to the left. So what happened? Imagine this was, oh sorry, if it was even allowed, which is not in binary. Imagine in this decimal numbers, right? You'd had this number you would be putting to the left, so you'd be putting the comma to the right, so it'd just be the 0 would go here, right? You're just sort of jumping. Basically what it means, if you shift to the left, you add zeros, right? If you shift to the right, you remove a 0. Or like whatever it is on this position, 0 in this case. So we have 8, 1 and 3 zeros, because it's like 2 to the power of 3, so 3 zeros. And we bit shift by 2 positions, so we add 2 zeros. In binary, what happens when we add 2 zeros? We add 1 0, we multiply by 2. We add another 0, we multiply by 2. So basically, let's test it. We're gonna turn this into an integer. This is the base. It's like base 2. 32, right? Which means what we did is we said 8 times 2 to the power of 2, right? Okay, and then, so it's like 8 times 4. Fantastic. So now we know what happens in this code. Basically, L is 8, and then we're gonna see, is L times 4 lower than 4? Yeah, right? Because 8 times 4 is 32, and N is 1040, right? We had it somewhere there. Yeah, 1040. So like, okay, cool. Well then, pass it on to this function. And then, you're gonna say, okay, you do some like calculations there, and assign this new value to L. So like bit shift and assign to L. So L turns into what value now? 32. And what check are we performing later? 32 times 4, so it's easier for me to think in powers of 2. To the power of 3 times to the power of 2, so to the power of 5, 35, yeah. And then to that to the power of 2, 1 to the power of 7, 128. So like 32 times 4, 128. Sorry, we're gonna note it here. Is it lower than N? Yeah. Execute. Assign this to L. And again, is what's 128 times 4? 512. Is it lower than N? Yeah. So it's still, we're gonna pass L, and currently our L is 128, to this function, and then assign 512 to L. But then as we go to the next condition, is 512 times 4, which is 2048, lower than 8? No, right? Because n is 1040, which is where it executes. So it doesn't pass 500, it doesn't pass our last value of L here, which is 512, and it doesn't assign L to 2048. So the maximum value of L we're passing here is not this, we don't reassign because this first condition wasn't met, is 128. Okay, so what do we know about this? We have this check if we're not exceeding the array size. So why are we getting in trouble? Well, so what does this check assure us? That this magic power of L never exceeds like at maximum, it can be L, like n can be L times 4, right? Because this is the condition we're checking. Our L is 8. Is L times 4 lower than, this is the condition we're checking, right? Is L times 4 lower than n? Yeah, pass it on. Reassign L. Is, again, the new n, so 32, times 4 lower than n? Yeah. Okay, assign it. Reassign L to 128. Is 128 times n lower than? Yeah, good. And then assign it to 512, but then this is when the condition fails, so 512 is never passed on. Cool, so we know what the maximum of L is, 128. And then, since I'm already dragging on, I don't want you to go through the whole journey with me, but if you go past this L in, and then you look at how it's used, I'll just briefly skim through it and we have a break. Well, then you can see that you're using it here. You're assigning in, again, L times 4 to M. I don't know what this M is for yet, but I don't care, because what I care about is how I access A. So I can see here like, oh, so this J is great on A, this index, J1, and then J1 plus 1, J2, blah, 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 and J2, J3. What is this J2, J3? Oh, J1 is L plus J plus L, J2 is blah, 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 blah. So I'm only interested in the highest number. So the highest index I'm querying here is like this looks like the highest number, right? Because this J3, just gonna use this, enter. Because this J3, what it basically is J2 plus L, and J2 is actually J1 plus L, plus L, and then J1 is J, so it's J plus L plus L plus L. So it's basically 3 times L plus J, okay? And then J plus 1 is my maximum index. J3 plus 1, right? Okay, so this is my maximum index I'm querying in this for loop. And then I'm checking, okay, what's the maximum number of J I'm getting? And then we can still reason about like how the J changes, right? So J changes from 0 and then goes by 2, 0, 2, 4, 6, blah, 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 until I reach L. And in my worst case scenario, what's maximum L? Maximum L is 228. So here, my maximum J index is what? 126, right? Because for 128, this condition fails. So my maximum, sorry, I'm just gonna add enters here. My maximum J is 126, which means my maximum index I'm accessing here, right, is I put this 126 as the worst case scenario to here, compare it with the worst scenario L, and get, I'm just gonna do it for, I think it's 511, right? So this is maximum index. Okay, cool. And then we would repeat stuff like that for other loops, right? To see how we access, how these value change. Because like here, okay, so this is like not a faulty, not a faulty scenario for me because 512 is within the bounds. Okay, what happens in the other loop? I do the same. I can see like, oh, it also has the same pattern here. J3 plus 1 is the maximum index. What's my maximum J3? Oh, it's the same as in the previous example. It's like 3 times L plus J. It's completely the same. We have it written down here. It's 3 times L plus J. But then what is my maximum J? And it's L plus M. So it's my L was the worst case scenario 21 to 8 plus what is M? Well, now we go back to what M was. Oh, it's L times 4. Times 4 because bit shift by 2. So this is, what is by 4? 512, right? And this is my maximum L. And this is, what's the value of this? 500. Let's use 512, 12 plus 108, 640. Okay. Oh, where am I? Sorry, what was I doing? Okay, so my maximum index, max J3, right? Max J3 is 3 times L, and L was 128, plus J, and maximum J is, we said, L plus M. So it's L plus M, and M was L times 4. So it's like 4 times 5 times L, 5 times L, and that's gonna be, but this was also L, right? So it's like 8 times L. Is it? 8 times L? 8, 8 times 128. All right, so this is 124. But what I forgot about is that actually my maximum J is this value minus 2, right? Because for this value, actually the condition is gonna fail. So this is like minus 2. So this minus 2. So it's like this. And then the maximum index I'm accessing is this plus 1, so 1023. Within the bounds? Yeah, it's within the bounds, cool. And we do the same for the third loop. And here, additionally, we have this K component. And what is K? So my maximum value is just like the one before, but plus K. And what is K? Well, K is, that's with M2. What is M2? 2 times N. What was M? I think I calculated it somewhere. M was L times 4. And I think like K is, so then it means K is, I'm just gonna speed it up here. Here, it gets assigned to 1024 and then goes plus M2, which is 1024. So this condition is gonna be immediately broken because 2048 is like lower than our N. Whatever, so later, here we can see that our J increases over our bounds because maximum J, actually, we're gonna do the same computation, but I did it for you before, so that you don't have to do it, is 1535. Okay, and then it's because basically, if we put all these things back together, that like max J3 is 3 times L plus J plus K plus L, it turns out that actually our maximum J3 is 12 times L minus 1. I just like made this computation for you. So like, 12 times L minus 2 what was that again? Sorry. This one, yeah, okay. So maximum index is maximum so maximum index is maximum J3 plus 1, because this is the maximum index we're approaching here. And this is basically, the calculation simplifies to this, 12 times L minus 1. So we're like, okay, so as long as we have 12 times L minus 1 samples is good. And our guarding condition was that N has to be lower than 4 times L. It should work, right? So like this is my maximum index, L, 12 times L minus 1, but the condition is N is greater than 4 times L. So that should all, sorry, not 4, but 16 in the end. I'm sorry, 2 to the power of 4. Why? Because we were at least 8, and then we're checking if L times 4 is greater than, but then after assigning, we're checking times 4 again, so 16. So our initial condition is L times 16 is lower than L, and then our maximum index should be this. So the logic in this freaking thing seems to be okay, and we've just lost some time of our lives. So what the hell is the problem? Well, then if we continue to reason about it, it turns out that this condition that we looked at here, here, only makes sense if N is a power of 2. Because this is when it exits on time. Because if we saw, so we were like reasoning about this. So L changes from being like 8 to 32 to 28 to 512 and so on. Always skips 1 power of 2. And then if N wasn't 1040, but the next power of 2, which is 2048, we would be able to access this index, right? So this condition was designed for numbers that are powers of 2. So we're like, all right. And actually, if you go back to the documentation of this library, it says that it's expected to be a power of 2. But I didn't think at the beginning to look at the documentation. So basically, where is this complex? Yeah. We're calling, like, let's see, we're calling it to CDFT, documentation of CDFT, complex discrete Fourier transform. Wow, data length, power of 2. You're like, right? So now the question is, how do you fix this? But where? Okay, so usually, this is a common problem in the audio processing world, right? Commonly solved by, okay, so we basically need, our data length is, this is actually twice the data length, right? 1040, like our data length is 520, right? But never mind, times 2, if it's a power of 2, it always works. Okay, 1040. But what we actually want to have is to have the next power of 2 of this, so 2048 samples, right? So what do we, like, we want to have more samples. Where do we take them from, right? To like stretch the sample? No, we usually just pad it with zeros. As we've seen here, for the short sample, the computation didn't fail for me just because this memory that I shouldn't have access to was assigned to zeros. And this is exactly what we're gonna do, but by design this time, so that it always works for everybody, right? And it's very common to be doing zero padding until the next power of 2. But now the question is, where did my code fail? Here. This is just like, where am I gonna do this zero padding, right? Because I wanna pad which data? Well, this data, right? And what is this data? It's whatever comes from our this source array, and the source array is our WAV file. So reading a sample, and we're gonna pad it. Should the framework do it for us? But then it may destroy our, if we do it, for instance, in the wherever we're gonna call into this function that requires this first argument to be a power of 2, right? If you do it here, it's gonna be surprising for people. We're destroying the data. What if they wanted to reuse this data for something else, right? Is it a good design decision to pad here for always?
Which data will be destroyed?
Sorry, again?
What is the data that will be modifying the X?
Exactly, right? So like the data of our samples. We have these samples. What if we padded zeros on top of it? Maybe it's fine.
But there we also have A that you could change.
Okay, so we just are changing A. Yeah, that's a possible solution. So we just prepare the A so that the A is padded with zeros. We could do that. Do you want to do it? I don't know, we could. That's a valid solution to accept, right?
What would be the output then? Would the user be expecting the size of the output?
Well, then, like, we can't even execute this computation if we don't have these data, right? So, like, we can't even use it. This is, like, useless. So we have to somehow assure that this X holds a data of the size, which is the power of 2, right? So, like, yeah, that's fair enough. This is a good example. We can just modify the A that we are creating for the purpose of these computations and make it the responsibility of the framework to pad the data for us. Or we're gonna, the solution that I suggested, it's on the branch called Fix of this workshop, is that we say, you know what? The client code, so the caller side, the application we're writing when using this framework, are responsible for preparing the data in the right format, right? Which is also a valid decision. We can say, it's on you, just give me what I need. But then, we've just spent a lot of time doing very nasty debugging. So we want to save people from doing that. So the bare minimum we can do to help people would be to like throw a useful exception here, right? Be like, don't even attempt at executing this when n in this example is not a power of 2, right? Also, when you look at this code, it is fragile in a way that there is no check whatsoever anywhere that X holds at least n elements here, right? So there's a lot to be like, to wish for from this code. It's not very reliable, right? Many things can go wrong and then you end up with super cryptic problems. So if you now check out the branch fix, or maybe if you want to do it yourself, we can fix this problem by basically, I would suggest, throwing a useful exception here and then going back to our example code and padding the data. But we can do it all after the break because this is like, I apologize. But you know, I hope like you saw some useful things here. There's like how you can actually approach debugging extremely cryptic code, which so okay, at the end, we have reasoned about values, we've learned about values, but I still don't understand how this algorithm even works, right? And I don't have to. I just have to understand what it wants from me to work, right? So that's the takeaway. It's like, you don't have to understand, like in this situation, I only had to understand the relationships between values, right? In order to be able to use it. I don't have to understand the whole algorithm. Maybe we can take it a step further and, you know, and try to understand it, but that's another few days. Right? So this is basically, yeah, I hope this was just useful to see how different things you can use to aid yourself in a debugging practice. And to summarize it, yeah, always remember you're in a conversation with a debugger, right? You're sort of like, it's a tool that's supposed to help you, not just scare you. So, okay, so what I wanted to point out is that like, let's not try to keep everything in the working memory. Actually, using pen and paper is a cognitive strategy called, you know, we're supporting distributed condition, which just means pen and paper extend our working memory, which is short term, right? We're not going to remember things. So there are just this like cognitive tools we can use and be aware of. So like no shaming in using these techniques. And always go back to like, what am I trying to do? What do I hold on to? There was not much to hold on to in the C library code, right? Like, no name is useful for me. I don't understand what's happening. So there's just pure values that I'm going to do. But I at least lowered my data set to be able to reason about it better. If you have higher level things to hold on to, like useful names, or maybe some useful Git history of like what people did when they do it, use it. It's all there to be used. But yeah, we were relying on these like lower level concepts, values, and their relations. And again, don't read code linearly necessarily. Sometimes you need to, but not always. Follow the call stack, go back and forth, try to understand what's calling what and why. And this is what we've been doing. All right. So I thought that the debugging session was going to take 40 minutes and it took an hour and a half. So I guess we're not going to do... Yeah, so we're not going to do a lot of live coding then, maybe for the better. So we're just going to maybe, let's just analyze the code on other branches instead. But before we do it, I wanted us to... Well, maybe let's start there. Let's look at the proposed solution to our code so that we can all see a potential fix. As I said, there's so many different options to do it. I'd like you to check out the branch, the fix branch. And then I'll try to rebuild it from VS Code. Okay. I want to run it, but I will want to go back to passing my the tone that didn't work. But before I do it, let's look at the changes to the file. Actually, maybe it's going to be even better to look at the actual changes, not at the end file. So as we said, one potential, idea how to solve this problem is to make changing the size of our data, padding it with zeros, a responsibility of the caller, which means I'm the caller. I call into the framework, right? My code is the caller. So this was my code that I wrote for reproducing this faulty scenario, and I'm just going to do the padding here. How am I doing? So as we saw before, the problem was that the number of samples we are passing here to this MFCC, which ended up being the size of this MFT, was in the power of 2. So I wanted this number to be different, but also what we saw, we want the size of this data array, right, that's passed to calculate, to be the same size or bigger, but ideally the same size. So I have to change these two variables that I'm passing. First of all, what I need is I need a function that runs up to the next power of 2. It turns out that this Aquila, I mean, we're assuming this is how it's pronounced because there's like a biker gang called Aquila, I think. But we don't know what the author is, if the other was referring to it, but. So it turns out that this framework has some helpful function which already have this implementation of, is this number a power of 2, give me the next power of 2. Let's take a look at them. Where is this? Here, functions, right? It has this change to DB, whatever. These are all useful utilities that we may find helpful when writing audio processing code. Okay, so the two that are interesting here for us is power of 2 or next power of 2. Why did I want to write something? Why did I write something custom here and not use next power of 2? Well, because next power of 2 returns the next power of 2 also for the numbers that are already powers of 2. Right? It checks, is this number a power of 2? Still, return the next power of 2. Do I want that? I don't need that. if my sample happens to be the size of a power of 2 already, I don't want to like pad it with, right, zeros. That's good enough already. So I just created this like round to power of 2. Maybe I would want to pad it still, but like for now, to fix this immediate problem, I just want to assure that if the length of my sample data array is not a power of 2, just like round it to the next one. So this is just, I'm using these helper functions, but I'm just like early returning the number if it is a power of 2. Cool. So now we say, okay, this is the number of samples. What is the next power of 2 of it? This, assign it, I just called it FFT size, right? Since we have discovered that this is what it is. And I'm gonna pass this number to the constructor of MFCCs instead of the previous, like the real actual number of samples of the data, right? Like here. So this is the first gene. Sorry? Yeah. And then, so I'm just like passing this value here so that the FFT size is initialized correctly. But I also need to do the actual padding. And how I'm doing this? Well, I have to remember that calculate accepts a signal, not a data array, but a signal, right? So I don't know if you remember, but if we look at the signature here of this function, it wants a reference to a subclass of a signal source. And it just so happens that WAV file is a subclass of, well, not so happens, it was designed this way, that it's a subclass of a signal source. But we can't just pass it data array, we have to have a signal source. So we're just gonna create one, right? Just like and pass our, initialize it with our new data. So this is why I'm creating this, sorry, where's this, here. So I'm creating this signal source here so that I can pass it correctly to the function. And there is a constructor of it that accepts the data and sample frequency. But how we're creating the data now is we're basically copying the contents of our WAV file. And then, so like basically what happens here is we say, go to the beginning of the WAV file and just FYI, the signal source, if you go to the definition of it, is implemented, maybe it's even mentioned here. Yeah, it's implemented to be an iterator. It's just a shortcut, so we don't have to take, right, this begin iterator of the data array. Like if we take if you call like begin on the signal source, it is the same thing. It basically, yeah, it's just like this thing is customized so that it can also be used as an iterator, which is just like a convenience thing. So I pass it the beginning, like the start of the data, say how many samples I want to copy, and this is actually how much of the actual samples I have, right? And copy it into the padded data. And I could also pass it like, well, like, and then like we can think, what happens with the remaining part there, right? I created this vector size with the intended size, the bigger size, the power of 2, but I'm only copying this data. I have to also initialize the remaining part to zeros, right? I do, but actually std vector does it by default. It's the default. If you don't pass it a value to initialize with, it just defaults to 0. So I don't have to do it. It does it for me. Right, so I'm just creating this new signal, using this data to create a new signal, and I can pass the signal to the MFCC calculate. And then when MFCC calculate receives our signal here, it calls to array, and it should have the intended size next power of 2. Well, let's see if it works. So I'm just gonna run this program first. Right. Okay, build it and then run it. Oh, exactly. I didn't provide it set up for running, oh, whatever, I'll run it from the debugger anyway, because I'll just want to explore some values anyway. And these are old breakpoints. Go forward. Just to check, we were here exploring these values here. Let's go further to, yeah, this more readable code. So we're expecting the value of n now to be a power of 2. Let's see what it is. Is it a power of 2? I don't know. But I'm gonna check in Python. So what's the best way to check if something is a power of 2? Maybe if I take logarithm base 2, it should return an integer value, right? So I'm gonna try that. What is it? Log 2? Is this how Python works? Do I remember correctly? No, shit. Import math. Yeah, okay. So just to check, power is base first or base first, cool. So power 2 to the power of 20. Yeah, okay, perfect. So it is a power of 2. Yes, everything should work. It shouldn't crash. Just double checking if I'm passing the right sample. Yeah, the long tone. Gonna finish correctly. Stopped here because it's my old breakpoint. Continue. The console. Looks like it worked. Fantastic. Just rerun it again without the... Yeah. Computes the coefficients, spits them out. No errors. Fantastic. So the padding worked, okay? And now, what do I want to happen if the calling side doesn't do the padding or doesn't do it correctly? Or maybe let's just manually change it. So if I actually, I don't know, subtract 1 from the size, and then build and run it, it's gonna build. Yeah, I wanna get a meaningful error, which says, exception has occurred, data size is expected to be a power of 2. Thank you, framework. You're telling me how to prepare my data. Great, right? And as I said, this is just one proposition to throw at useful information for the framework users before letting them get into trouble, right? Okay. So now, after seeing how we can potentially solve this problem, so this is where I'm throwing this exception. I am contributing to an existing framework, right? And I'm quite meticulous. And I like all the code I'm adding to be tested, right? So that if somebody in the future goes through my code and says, must be all out, I'm gonna remove it. That's whatever, right? Then I want them to be notified that it was intended to be there. It wasn't added on a whim. It was well thought through, and there's a test that's going to tell them why. Because I think if code base is well tested, and actually this code base is quite well tested. If you look at the test folder here, where are the tests? Here. They're like folders for each, this is data, folders for each class, everything's well tested. Even this transform, like the function, even the functions that we were using are well tested. It's next power of 2 and stuff like that. So this is also one of the reasons why we chose this library, because it's actually pretty well tested. And I want, was this? Yeah, was I here? Yeah. And I also think that if a code base is very well tested, the tests serve a purpose of documentation as well. You can reason about the decisions made in the code by looking at the tests. I think it's extremely useful, and I'm very opinionated about this. So, yeah, I added, coming back to the actual problem. So I added this code, and I'm gonna offer, like suggest the authors to get it merged. So I'm just also gonna make sure that my intentions are well tested and documented, right? So here, if it was up to me, I would actually write a more useful name of a test, but just following the conventions used in this file. I just basically was very short with it and just said what I'm immediately doing. So basically what I'm doing here is like I'm creating some data with like size, which is not a power of 2, 127, the next power of 2, 128. And when I'm expecting to be calling this FFT code, which is just as a reminder, this function, right, where we added this exception. If I pass data here, it's just a pointer to the, well, basically just expects a C array, right? That if the size of it, or like the size of the FFT, this like function was, like this object was created with, is not a power of 2, I want to throw. And a lot of like testing frameworks have this useful macro that also like lets you say, if I execute this code, I want this exception to be thrown, right? So I'm just creating this FFT object, and then I say, pass it this data, which is like I'm passing, right, like sort of dereferencing the first element of my vector, which is, you know, a trick to make it look like a C array, to like giving it access to the like raw data inside, and then it should throw. And now I would also want to run my test and see if it throws, which is maybe what I'm going to do from command line. Why not? Aquila has make, I think, Aquila test is the target. Oh, great, or maybe I won't do it. Can I do CMake, just change the target to tests and run, okay, just build it. Cool. And now I'm gonna run the tests. Yeah, something's going. Where's mine? What is it? Well, what file was it in? Or FFT, argument validation, passes. Fantastic. Okay, so just to give go back and like let people know what is happening right now, I wanted to like briefly mention what tests are and what types of tests there are. So for instance, like when I worked at Ableton, a part of our recruitment exercise is to, well, we ask people to solve a problem and provide unit tests with it. And a lot of people straight from college are like, what's a unit test, right? So this is why I'm just gonna add some context. Well, it's what you've just seen, but I'm just gonna explain what you've just seen. So basically, when you have code, it can be tested at different levels. Unit test is a test that tests ideally everything in isolation, right? And these pictograms here are trying to depict that if you're building a plane, unit tests would be things testing each particular element of a plane separately. A wheel separately, a wing separately. Is there like a computer inside that works correctly, a different suite of tests? So this is unit testing. Integration is when you see if elements work well together, right? So it's like if the plane lands and then the wheel presses on the ground and it presses like back on the plane, it doesn't fall apart, right? So this is an integration test to see like all components coming together, does it still work? Not so obvious. And acceptance is basically when you see, you act like tests act like a user. Does it fly, right? Can I get in and fly there and actually come to ADC in one piece, right? So basically, there are more types of tests, but these are probably the ones you're gonna hear about most often. And then also there's like a sort of like blurry line between unit and integration tests. It's like you can be very particular about being like, no, unit test only tests one unit, one class, and whatever. Where's the line between testing? You know, it's like testing two classes, already an integration test. You know, it is. Does it belong to one component? And some people refer to it as unit test. So it is a little blurry, but yeah, but that's the gist of it. And there are different testing frameworks. I'd say the most popular ones are Google Test and Catch2. Google Test is quite big. It's very powerful, but it's a very big dependency if you're building a new project. Catch2 is just like a header library, so this is why it's gained popularity, because it just like drop a header in your repository, added, like, you know, it just gets fetched. It's like extremely easy to edit.
They're changing it now, unfortunately.
Oh yeah? Damn.
We did it last time in the class meetup.
Okay, Rachel is saying they're changing it now, and I don't know, and it's a bummer. Yeah.
Leah managed to find that old header, so we could still use it.
I see. Well, but then I still hope it's easy to integrate with the build system. And it's not, the dependency is not as big as... Exactly, because Google Test is very big to download and then slow to build. Anyway, this library that we're using is called Unit Test++. I never heard of it before using this library, but the beauty of these frameworks is that they follow similar patterns. So you should always find your way around them, depending, like, you know, when you start a new job and you're used to using Catch2, but this company uses Google Test, you'll probably be very quick to wrap your head around it. This is like documentation that's very, didn't make it into a link. That's very useful. This is what you would always refer to. What is it? It's called macro and parameter reference, and basically what it means is that it tells you what macros, because all of these names are technically implemented as macros, you can use to write your tests. And what it means is that when you open a file, let's just see this one file with tests. Tests, or what was that? Where's the file I added? I don't remember. Here? Yeah. So basically, if you create a, how would you call it? Some sort of scope. Or like, well, basically like a macro, but like this, yeah, looks like this. Starts with test. It's gonna be found by the testing framework and added to a bunch of things that need being executed. Suite is just something to group tests together. And a lot of testing libraries let you not run all the tests all the time, but like one suite at a time or a separate test at a time. Unfortunately, this unit test ++ library, I didn't find a simple way of doing that, but we have so few tests that it's okay to just always run all of them. Okay, so what I wanted to, so these are just macros, and they're always gonna be similar, but in order to understand why, let me show you what the rough sketch of every test always is. Well, you start with a setup, you perform an action, and then you perform a check. Let's see it in practice. So here, this is not a good example, but let's look at our test. Okay, so here we perform the setup, right? This is setup code. We create some values that we're going to be using, because the action that we're testing and that we actually want to perform is this one. No, sorry. Actually, the action is here, right? The action is here, but we want to check if it throws, so it's a little like combined together. But normally you would have an action and then perform a check at the end. And the checks, maybe we have something better looking. Like, yeah, usually look like, oh, check equal, check array equal, and stuff like that. So you basically like see if like this value, which is the expected value, equals to this thing we just generated, basically, right? So here we're like, oh, we're checking if this function produces the result that we expect. We expect it to be of this value, right? And for many people, it's a little confusing that like you're always told not to use magic numbers in the code, right? To always assign them to variables. In tests, you actually sort of want to use explicit values because many times you find yourself in a loop that you're like, oh, I want to test if this function produces this number. So for instance, in our test, right? If I wanted to test like two scenarios, say, okay, this test should fail, but if I put 128 here, it shouldn't throw, whatever, right? So like I'm just gonna remove this. And if instead of using 128 here, I said, oh no, I shouldn't be like using this value. So I'm just gonna see, I'm just gonna keep it as 127 and then say that the new size is like whatever the function was called, power of 2, right? Like find me like next power of 2 and then the size, blah, blah, blah. So many times basically what people do is they generate numbers that this function, sorry, like here, are going to be generated here. So basically, people like go in a loop that they test if a function produces correct output by using the same function to produce this output you test against. No, it's better to use like, this is the number, 1048 or something, right? Because many times you're going to catch yourself being like, I'm calling a function that produces this output and this other function I'm testing also uses the same helper function. Doesn't test anything. If the function that produces the output is wrong, your test is always happy, right? So it's good to put like, be explicit about the numbers in tests. It's completely fine. Okay. So this is testing very roughly, very quickly. We spent a lot of time debugging, which I hope was somewhat useful for some people in many ways. But so we're not going to do the modifying experience. Please feel free to check out the modifying branch. Do I have it open somewhere here? Here, where I wanted to, like, maybe you can do it as an exercise at home. I wanted to ask people to move the responsibility of the caller, of the calling code, to prepare the correct size of a vector to the framework, as suggested by one of you, right? The implementation I suggested here was just to basically offer like a method, helpful method in the WAV file implementation to pad the data automatically. Do you want it? Do you not want it? Because like it's optional to call it. So you only call it when you know that you're not gonna need your original data anyway. You're always gonna have it padded. Just a suggestion. And then we also tested. And this test actually presents better what I meant. We set things up here, right? We perform an action, we perform checks. This is how we write tests. Yeah. Right, like please feel free to like explore this branch or try to write it on yourself. I think it would be an interesting exercise. Also providing, thorough testing. So for instance, I moved our function round power 2 to the framework, since I'm going to be using it there now, right? So I added it to this like as an additional option to functions. So I needed to test it also for functions, right? So just getting used to this sort of practice. Okay, so just to wrap up, yeah, just a reminder to always going back to what your intentions are when doing things. Just getting yourself back. What am I doing? What am I doing? Should I be looking over there? Is it a distraction? Cool. We won't do test-driven development, so sorry, that's for a different workshop. I would like the benefits of test-driven development are similar to the benefits of having tests at all. As I said, having a lot of tests can be a good source of documentation, and it also helps you find entry points to the code base, because when you don't know how to write a new feature, it's sometimes helpful to like express the end goal as a test. And let the compiler guide you, let your tools guide you. So like, what's missing? Oh, this call is missing. Okay, I had this call. And it's like, what's missing? Okay, this. Oh, so it's actually nice. When I started working on the push team at Ableton, it was the integration layer between hardware and the communication layer between this hardware and Ableton Live was written in Python. And I think people writing in like dynamically typed languages tend to test more, since like if your errors are caught by the compiler. And it was a very well tested part of the code base. So this is how I was like, when I was new and I didn't know how to implement something, I was just write a test. So he's like, I want this to be displayed there. I have no idea what to poke to get there, but the test was guiding me. Oh, you have to put it there. You have to put it there. You're missing this component, which was very helpful. Cool, and when you develop with thinking, when you keep testing in mind while developing, you actually end up having code that's loosely coupled, more cleaner, you don't come up with premature abstractions. Surprisingly, it's surprising how different the interface ends up looking as opposed to just whiteboarding something. Many times, not always, but many times it's true. Okay, just to quickly wrap up. When it comes to code design, and we've already had this conversation about how to design our solution to our problem, solution to our bug. We saw two potential solutions, right? You keep the responsibility of the caller, keep the responsibility of the framework. These are just like one example of a discussion you have while thinking of the code design. But there are many other things that you would want to consider, and there are no good or wrong answers. It's always like, just think of what you're doing and why, right? So most of the projects should have, well, most of the projects you're working on in the IT world in general, of course it's domain specific, are going to prioritize maintainability. What does it mean? It means when it's a long-lived project, there's a lot of legacy code, and new contributors are joining often, it's better if the code is easy to read and reason about, right? Basically, you think about code design as dealing with complexity, right? If a particular part of code is going to be read often, it better be easy to understand. If it has to be cryptic, hide it in the framework, right? It's better. Some people will have to deal with, I don't know, who deal with like real-time applications who are like are really critical or have like limited hardware resources are going to prioritize performance. And maybe this code is going to be more cryptic because the C library we saw is designed for performance. It has to be a fast Fourier transform, right? It's very cryptic. So we would hope for more documentation, for instance, right? Like a better entry point to it if we have to maintain it sometime. So basically, going back to thinking about maintainability when designing your code, you can also think of different like sub areas of it. Like when you write code, you think about the readability of it later, scalability / extensibility of coherence. And what does it mean? Well, reading code, as we saw, can be very demanding because when we don't understand something, it brings this like cognitive load on us, right? And we want to spare people that because at the end of the day, it loses your company money if every single person has to go through the same painful process of understanding something. So there is, people Prioritize simplicity over quirkiness. I had a manager at Ableton who used to work at Google before, and he said it's like they were really particular about this practice. Just like fancy algorithms were not welcome. I myself used to be a big regex fan, and when I quit my previous company, nobody knew how to like maintain my regex validation code, and they wrapped it in 3 conditional statements. I'm not proud of it, right? It's not good. It wasn't a good decision to use something nobody can understand, right? Okay, well then you can help people out by giving meaningful names. And all in all, when the code is very easy to read, sometimes people refer to it as self-documenting code. You don't even need much documentation when it's just all so straightforward. When it comes to scalability, you can think also about it from different angles, but basically what it means is that like when the size of your data changes, your application can handle it. As we saw, like our application didn't handle different sizes of the data and didn't let us know about this, but like it could handle small or large samples, that's fine. Also, when you like want to integrate more components into it, you're going to make sure that it's easy to integrate new components, right? So you structure your code in a way that every component is sort of like, it's called loosely coupled. There are no strong dependencies between them. And when it comes to coherence, it's really good. Like when you spend more time with a code base, you start to understand it better. And it's good to have practices that are going to be similar across it, right? So, so that you know, like, oh, this is how we do things, so it must be this. You know what it means. In Aquila, everything tries to be an iterator, right? So you're just like reading about it easier later. Or like almost everything is modeled around the concept of a signal source, right? So you're just like, oh, this is a concept. Okay, I know what it is. I know what it is. Like, right? So like you learn one concept and translates, super useful. But this is also why some people in code review are going to be like, oh, this is not how we do things. And maybe it's better not to argue, just like stick with how, well, it's not always true that we should stick with old practices, but sometimes this is a reason also, it's coherent. And coherent code style, right? This is why linters are so useful. You never have to argue about structuring code anymore, just have a linter to do it for you. And then it's coherent. But yeah, as I said before, when you prioritize performance, try to hide the complexity. So the code that's being modified and read often, preferably wouldn't be the complex code and like cryptic code. But if you can't avoid it, just document it well. Yeah, in our case, deployment is just basically publishing our changes to GitHub. Please feel free to experiment or just like see how the workflow works. Create new changes to this library, create a new branch, and submit us a pull request. We don't mind on this repository if you want to see what the deployment would mean here. Deployment may mean different things in different projects, but in our scenario, this is what it would be. Basically, that's all. Sorry for tiring you out during the debugging session. I hope you could see, well, what many times you have to deal with in a real-world scenario, especially when dealing with big, large legacy code bases.